All right. Yes, yes, and there, and there. Any questions? Might as well get started.
So the math lab didn't want step, what was it, C or whatever? It actually wanted it all taken out. So I found that on the first one I came up to, on the difference quotient.
Oh, okay. Well, good.
Lamo! Knock it off! Poppy, you too. Where the hell did my homework go? Lamo, stop. Oh, okay. Now where did this stupid home?
Ooh.
Are we still in the phase of asking questions about the previous homework, sir?
Yes.
Excellent. I would like to ask about 1.4, number 14.
1.4, number 14.
Yes.
Let's see, John. The one with the K?
Yes.
Okay. Cool. Oh my goodness. Let me see. So 1.4. Perfect. Let's go laptop. I know you hate me today. 14. K is x plus 5 over x minus 5. And they give us k squared minus k equal to 20. Okay. So they basically already did U-substitution for us, but use k instead. So all you have to do is factor this equation. So you get k squared minus k minus 20 equal to 0. And then this would factor to k minus 5, k plus 4 equal to 0. K squared, 4k minus 5k, we're good. And then K would equal 5. And K would equal -4.
-4.
Good so far?
Yes, sir. So far, so good.
Okay. Then we bring in what K was. K is X plus 5 over X minus 5. Set it equal to 5. And then X plus 5 over X minus 5 equal to 4.
Did you mean -4, sir?
Or what do I do? Yeah, there you go. -4. Good. And then you're going to multiply those denominators to the right side. So X plus 5 equals 5 times X minus 5. And X plus 5 equals -4 times X minus 5. And just solve for X. So 5X minus 25 and -4X plus 20. Whoops. And then I'll move 5X over. Minus 5X gives me -4X. Minus 5 gives me -30. Then add 4X, I get 5X. Minus 5, I get 15. Okay. Then divide by -4. You'll get 30 over 4. Divide by 5, you get X equals 3. And then this would reduce to 15 over 2.
What dictates as to what on the second part right where you have the X plus 5 equals 5X minus 25? What dictates of where you start? Like if you take the left side, move to the right, or move the left side to the right, or right to the left?
Nothing. You can move your X's to the right if you want, and you can move your X's to the left.
That is interesting because I did that before. I was always moving everything from the right to left, and my left tutor always counted it wrong. And I had to redo this particular problem twice in order to get it right at the end.
So you were probably right because I worked this question out with another student today. And so say, for instance, how we got 15 over 2.
Yes.
It didn't want 15 over 2. It wanted 7.5.
Oh, that's right. Yeah, I was having a problem with with the decimal point. I got you.
So you were probably right on your first attempt, except there's that lovely blueprint that nobody likes to read. I don't even read it. So we were trying to figure out what we did wrong, but it wanted a decimal answer.
I see. Okay. Now I remember. Okay. Thank you so much for clarifying that.
Yeah. So you're good. Yeah. My math lab is stupid, but if that ever happens and you submit your work and you don't want to attempt the homework again, and you know you have the answer right, just submit your homework, upload your work, or just email me, be like, hey, I have this answer right, but it wanted a different input. I couldn't go in and give you credit for it.
Okay, understood.
Yeah.
One of the weirder ones was it asked for 2 decimal places, but one of them it wanted to round up to just one single decimal place, and that kind of threw me off.
Yeah, it's dumb, but if you have the right answer, like I said, if you upload your work, you can comment on your upload saying, hey, I have number 5 right, but it counted it wrong, and I could fix it for you. Because like I said before, my math lab is definitely picky. Okay. Attack my ugly K's. I saw that. Jessica Reyes, number 6 on what section?
1.4.
1.4, Jessica.
Before you guys continue, can anybody tell me how I could add like an icon to my name, like other people do with like pictures or whatnot on the Zoom?
I think you have to go to the actual Zoom website to do so.
It's account anchored. Okay, I got you. Thank you.
Yeah. Okay. Number 6 on 1.4. The one I'm looking at is giving me 8x to the fourth. You have different numbers?
No, that's right.
Okay. 8x to the fourth minus 2x squared minus 1 equal to 0.
Yes.
Okay. So we can do this by U-substitution. So u would take care of that term and u squared would take care of that term. So what we would end up with is 8u squared minus 2u minus 1 equal to 0. All right. And I don't know if this is factorable, right? Or maybe it is. Let's see. If I did the factors of 8, maybe, let's see. Yeah, 4u and then plus 1. No, yeah, plus, no, I can't do 2. So that would have to be like plus 1 and then 2u minus 1. Maybe that might work out. Let me see. That'd be 8u squared negative 4 plus 2, negative 2, and negative 1. Oh, yeah, there we go. Factored. All right, you good so far?
Yes.
Okay. And then you'd set these equal to 0. And we'd get 4u equals negative 1, 2u equals 1, u equals negative, negative 1/4, and u equals 1/2. But if we look back, u was x squared. So this becomes x squared equals negative 1/4, and x squared equals 1/2. Okay, cool. Well, in order to get rid of that square, what would you do to both sides?
Multiply?
Well,
No.
we want to get rid of that.
Square root.
Square root. And
Yeah.
what's wrong with the first one already?
There's a negative?
So can you square root a negative?
No.
No, right? So this is out because that gives us imaginary numbers.
Got it.
And then for this one, you square root both sides. That becomes square root 1 over square root 2, which becomes 1 over the square root of 2. But you can't leave it like that. You have to rationalize it, which means you would multiply it by square root 2 over square root 2. And your final answer would be the square root of 2 over 2.
Got it. Thank you.
There you go. Cool. Any other questions before we get started?
Can we go over number 20, please?
Number 20, same section?
Yes, sir.
I'm assuming that was Catherine, right?
Yes.
All right. Number 20. Oh my goodness. Why do I give these problems?
I admit I had the same problems with the same number section, so I would like to hear this too.
All right. 20, I have x times x squared minus 2x to the 1/3, and then plus 4 times x squared minus 2x to the 4/3 equal to 0. Okay, well, do you want to go about this by U-substitution or by normal factoring?
What would be easier in this case?
I
Because
would say normal factoring.
Okay, because I think like the problem I had is the fractions, and then also when I was trying to use the help button on this one, it was like trying to take out multiple stuff at the same time, and it kind of got me a little confused.
Oh man. Okay. So if we're going to factor this by normal means, we look for the common factor, which is going to be x squared minus 2x, right? And which one has the highest power? I mean, sorry, the lowest power.
It would be the
1/3.
first term.
Yeah, 1/3. So what we're going to do is we're going to factor out an x squared minus 2x to the 1/3. All right. And if I take this factor from this term, they're going to cancel, right?
Except for there's an x in front.
Yes, very good. And there'll be an x in front. Plus 4. And now this term from that term, what's going to happen?
So we need.
So I'm going to show you what we're actually doing here. So remember, factoring, you're essentially dividing the term out from everything, right?
Right.
So when I take x squared minus 2x to the 1/3 out, here, side work. This is what we're looking at. X squared minus 2x to the 4/3. And when I factor that out from it, it's going to be over x squared minus 2x to the 1/3. Now, from your exponential properties, if you have the same base, what do you do with your exponents?
You can subtract them, right?
You subtract them. So you get x squared minus 2x to the 4/3 minus 1/3, which will give me x squared minus 2x to the what power?
Third?
3/3, right?
3/3, yes.
Which is just
1.
1. Yay. Now we're going to bring that in. So that's going to be right here. How's that?
It makes sense.
All right. And just know, if you ever need to check your factoring process, just distribute it back in. And if you get back to the original problem, you have factored it correctly. Okay. So now we have a lot of cleaning up to do, right? So x squared minus 2x to the 1/3. I'll keep that bracket there. You have to distribute that 4. And still more cleaning up to do. And I'll just rearrange this as 4x squared minus 8x. Oops. No, that's just 4x squared minus 7x, right? 4x squared minus 7x, yes. Okay. And then in here, what do you notice you can factor out? Whoops. Oh yeah, from 4x squared minus 7x, what could you factor out?
An x.
An x. So I'm going to put that in the very front here. X squared minus 2x to the 1/3 times, and now I'm going to just write this as 4x minus 7. Yeehaw, guys. Okay. And now we can set each term equal to 0. So you'll get x equals 0. X squared minus 2x to the 1/3 equals 0. And 4x minus 7 equals 0. Hey, one answer already. All right. So for this one, to get rid of that 1/3, you're going to have to raise both sides to the what power?
1/3 power.
Not the 1/3, the reciprocal.
Oh, the reciprocal of it. Okay.
And you'll get x squared minus 2x equals 0. You can take an x out. You get x times x minus 2 equal to 0. And what are our two answers from this one?
0 and 2.
0 and 2. And then the last one, 4x equals 7, x equals 7/4. Yeehaw. You only have to put 0 once. Don't put it twice. $1.4 due today. Yep. Number 18 on 1.4. What's 1 and 3?
I was answering to some of the questions that you were answering. Or
Oh, okay. I was like, oh, okay. Perfect. Wonderful. I was like, what is that? Okay. 18 on 1.4. And then I'll make that our last one so we can start lecturing. All right, 18 on 1.4. Okay, cool. All right. You have v over v plus 1 squared plus 3v over v plus 1 equal to 18. Okay, so we're going to do some U-substitution on this. The first one's going to stay the same, v over v plus 1 squared. But for this one, I'm going to rewrite it. I'm going to rewrite this as 3 times v over v plus 1 and move the 18 over. So 3 times v over v plus 1 is the same as 3v over v plus 1. Okay. And now we will use U-substitution. And U is going to cover all of that, which means U squared will take care of all of that. So you'll get U squared minus 3U minus 18 equal to 0. Factor, I believe you'll get U minus 9 and nope, not 9, 6. Oh, that's 9 and 2, sorry. U minus 6 and U plus 3. So U squared 3 minus 6, negative 3, and negative 18. All right, how are we doing so far? Good, all right. And now U equals 6, U equals negative 3. But U was V over V plus 1. And now all we have to do is solve for V. So again, multiply those denominators to the right, and you'll get V equals 6 times v plus 1. V equals -3 times v plus 1. And then solve for v. I'll move that v over, sure, -6, -5v equals 6. Add that 3v, 4v equals -3. And then v equals -6/5. And v equals -3/4. Yeehaw. Okay, cool. So if we have time left over, we can answer more questions. If you really need some answers, some questions answered, I can make a separate breakout room and put you with Carl. So if you want to do that, let me know. All right.
Down for that if anybody needs help.
Yeah.
As if I had a choice, but I'm just letting you know I'm down for it.
You can deny it, Carl. You can be like, no, I'm not doing that. All right. Nah. After class, like I said, we might have some time left over, but after class, I'm eating dinner. All right, so here are the notes we are going over today. We're doing 3.2. So there it is, right? 3.2. So we're going to do that. And we're doing 3.3. Which is there. There we go. So download those and just follow along. If my laptop doesn't blow up, we'll be fine. It's getting super hot today. Okay, so we start with 3.2, which isn't that big of a section. This is just called the graph of a function, and it just wants us to recall what a function is. Remember, a function exists if every x in the domain has exactly one y in the range. And if you're ever given the graph that could possibly represent a function, one way to tell that it's a function is by using something called the vertical line test, which means if you use a vertical line test, if you draw a vertical line through the graph and it only intersects the graph once, then you have a function. If the vertical line intersects the graph more than once, then you do not have a function. So this is pretty fun because all we have to do is decide whether these are functions by drawing a vertical line through it. So for the very first graph, if I draw a vertical line through it, I only intersect it once, which means you have a function. All right, the graph to the right, once again, if I draw a vertical line anywhere through it, I will always only intersect it once. So again, you have a function. And then the third graph, if I draw a line through this graph, I intersect it twice, meaning this is not a function. And then the very last one, once again, if I draw a vertical line through it anywhere, I will always intersect it twice. So once again, not a function. Oh man, that was easy, right? So if you're ever given a graph that could possibly represent a function, use the vertical line test to see if it's an actual function. Okay, easy for now. Yeah, for sure. 3.2 is all easy because this is the, what is that? No, there's 2 more pages. Sorry, I was like, this is the last page. No, it's not. Okay. So the next example is just obtaining information from a graph. This just wants you to learn how to read a graph. So the very first question we have here, I'll say 1, it says, what are f of 0, f of 3 pi over 2, and f of 3 pi? Basically, what this question says is when x is 0, and when x is 3 pi over 2, and when x is 3 pi, what are the values of y? That's all this says. So look on the graph when x is 0, and what is the value of y?
4.
4. Good. Then look on the graph where x is 3 pi over 2, and what is the value of y?
0.
0. And then look at the graph where x is 3 pi, and what is the value of y?
-4.
-4. That's it. Not bad, right? 2. What is the domain of this graph? Remember, domain deals with x values. And if you ever state domain, you start with the smallest x value and end with the largest x value. So my domain, where do I start? What number?
0.
0. And I stop where?
No, 4 pi.
4 pi. And brackets, because we're including, because these points are defined. Okay. Oh, different color. Range. Range deals with y values. And just like domain, you state the smallest y value and end with the largest y value. So what is my range of this function? What's this?
-4 to 4.
Good. -4 to 4. All right. Now this next question says, list the intercepts. So give me all the x-intercepts and give me all the y-intercepts. And remember, x-intercepts lie on the x-axis. So what are my x-intercepts?
Pi over 2.
Oh,
Good. You good. Pi over 2. Where else?
3 pi.
3 pi over 2.
Yeah, sorry.
Where else?
5 pi over 2.
5 pi over 2. And one more, right?
7
Right.
pi over 2.
7 pi over 2. Good. And then what are my y-intercepts?
0. Oh, no, 4. I'm sorry.
You got it. Well, if you're going to say 0, 4, correct.
Okay.
Good. So remember, x-intercepts lie on the x-axis and y-intercepts are on the y-axis. All right. 5. How many times does the line y equals 2 intersect the graph? Well, y equals 2 is what type of line? Vertical or horizontal?
Horizontal.
Horizontal. So if I drew a line y equals 2, how many times would I intersect this graph?
That'll be
4.
4.
4. Good. And then 6. For what values of x does y equal -4? So what this is saying is when y is -4, what are my values of x?
Pi and 3.
Pi and 3 pi.
Pi and 3 pi. Good. Last one. 7. For what values of x is y greater than 0? So whenever you see f of x, remember that's the same as y. So this says, for what values of x are we above the x-axis?
Four.
So we're looking for x values.
Oh, sorry. X values. Y greater than 4. 0 2 pi, 4 pi.
That's it. So if you ever see f of x greater than 0, that just wants to know where are we above the x-axis. And at those values of x,
Wouldn't that be a range since
0,
it's a continuous graph?
2 pi, 4 pi. What's that?
I said, shouldn't that be a range of values since it's a continuous graph?
Well, yeah, like what? All of these values?
Yeah,
No, not this time.
not this time.
Only
Okay.
the ones you can see. That's it. 0, 2 pi, 4 pi. Okay. And that's how you read a graph. Any questions on that? All right. What is that? Okay. Now this is the last page of 3.2. Look at that. Easy, right? So consider the function x plus 1 over x plus 2. Find the domain of f. Well, what type of function is this? What's the name of this type?
Linear?
Linear is if it was y equals x plus 1.
Is it rational?
Rational. Good. Rational. And how do you find the domain of a rational function?
Set the denominator equal to 0 and then solve for x.
There
and
you
it's
go.
not equal to that.
So you set the denominator equal to 0 and you solve for x. But we can't be equal to that because it would make the denominator 0, right? Perfect. If it wanted the answer in interval notation, what would you write?
Negative infinity to -2, both in parentheses. Then union -2, comma 2, parentheses, and then union 2,
Well,
infinity.
just there's only one
that's
number.
Right. It's only
You're
-2.
good.
I was looking
You're
at the
good.
other one.
All right. That's it. That's domain. Second one. Is the point 1 1/2 on the graph of this function? How would we find that out?
Would we plug in back those values, like for say, like since 1 is x, then we replace it where the x's are?
That's it. Plug in 1 for x. It's giving you a point, and remember points are x and y. So plug in an x value and see if we get 1/2. You get f of 1, which would give me 1 plus 1 over 1 plus 2, and we get 2/3. So is 1 1/2 an actual point on this function?
No.
No. What point is on this function?
1 2/3.
There you go. Yeehaw. Okay. Third one. If x is 2, what is the value of f of x? Oh my goodness, what do we do here? Plug in what?
2.
That's it. 2 plus 1 over 2 plus 2. We get 3 over 4. So the point that is on this function is 2 3/4, right? Not bad. Now this says, if f of x is 2, what is the value of x? This time we plug 2 in for what?
For y?
For y. So you would get 2 equal to x plus 1 over x plus 2. And then solve for x. Multiply that to the left side. And you'd get 2 times x plus 2 equal to x plus 1. 2x plus 4 equal to x plus 1. Move your x's to whatever side you prefer. and I would get x equals -3. Meaning the point on this graph is -3, 2. Everybody good with that? It's too much candy. There we go. All right, got the last one. What are the x-intercepts of this graph? So how do we find x-intercepts? What is the method for doing that?
You said x equal to 0.
Not x, but
Y.
y. Because if
Oh, that's on Y,
x-intercepts,
yeah.
there you go. If
I got it.
x-intercepts lie on the x-axis, what is the value of y on the x-axis?
0.
0. So to find an x-intercept, you let y equal 0 and you solve for x, which means you would get 0 equals x plus 1 over x plus 2. And then you'd multiply that to the left, but you would just end up with 0 equal to x plus 1. Therefore, my x-intercept is what value?
-1.
-1. Yeehaw. And the point would be -1, 0. And that finishes 3.2. Oh my goodness. Wow. So, any questions on that section? You're like, I got this math thing, right? Okay, so that was 3.2. Let's move on to 3.3. Okay. Three point three is about the properties of functions. So we're first going to start off with learning what an even function is and an odd function is. So to be an even function means you are symmetric about the y-axis. This means you can reflect any points over the y-axis. So if you have a point xy and reflect it over the y-axis, you would have the point -xy as well. So that would be graphically. So an even function graphically is symmetric about the y-axis. And algebraically, if you are an even function, if you plug in -x for every x, you will get the original function back. So to be even graphically means you are symmetric about the y-axis. And to be even algebraically, if you plug in -x to the function, you will still get back the original function. So let's actually look at something that is even. So I'll just page hop. I'll go back from 1 and 2, 1 and 2. So let's look at problem number 1 here. So we want to check, all we want to check here is if we are algebraic, if we're even algebraically. So all I'm going to do for this function is plug in -x. If I plug in -x, I'll get -x squared minus 5. And -x squared is going to return to me x squared minus 5. Now I ask you, did we get the original function back?
Yes.
Yes. So this equals f of x, which means we are even. So algebraically, this is what it means to be an even function. You plug in negative x, you get the original function back. Okay. Now let's talk about being odd. If you are an odd function, then you are symmetric about the origin. So the origin, remember, is the point 0, 0. So if you're symmetric about the origin, you'll have a point xy here, and you can reflect across and have a point negative x, negative y across from it. So this is what it means to be odd graphically. Now, to be odd algebraically, if you plug in negative x for every x, you're going to get returned the original function, but all the signs will have to change. So to be odd algebraically, plug in negative x for every x, and all the signs must change. So again, let's go look at an example of that on the next page of what it means to be odd. So just go here. Boop, 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 boop. That one's, nope, not going to work. This one, number 3. Okay. So for number 3, I'll do the same exact thing. I'll take negative x and plug it in for every x. Okay. Well, negative x cubed means negative x times negative x times negative x, which is still going to return to me negative x cubed. So what this returns to me is negative 5x cubed and then plus x. Now, in order to be odd, all the signs must change. Did all the signs change on this function? Here you had positive 5. Now we have negative 5. Here you have negative x. Now we have positive x. So again, did all the signs change?
Yes.
Yes.
Yes. Good. So this means that this is equivalent to negative f of x, which means we are odd. Now, in case you don't know if it's odd just by looking at it again, you can always check your work. So here we can check by just doing negative 1 times your original function, negative f of x. So I'll have negative 1 times 5x cubed minus x. Distribute that negative 1, and we'll get negative 5x cubed plus x. Does this look like the answer we got when we plugged in negative x? Yes. Good. So that's one way you could check your work. Okay. Perfect. All right. Back to the first page. Okay. So just to go over it again, even graphically means you are symmetric about the y-axis. So I guess I could have drew a graph for that, right? I could have said if you had a point xy here and you reflect it, you'd have a point negative xy over here. So you can reflect across the y-axis. Algebraically, if you plug in negative x, you'll get the original function back. And then, to be odd, graphically, you are symmetric about the origin. You flip over 0, 0. And algebraically, if you plug in negative x, you get the original function back, but all the signs must change. Okay. And just like I've been saying, a function is even if and only if its graph is symmetric with the y-axis, and a function is odd if and only if its graph is symmetric with respect to the origin. Now, looking at the graphs below, based on our even and odd knowledge, let's look at graph 1 and tell me, is it even or odd? Or neither?
Would it be even?
Even. Good. This is even. Because does that look symmetric about the y-axis?
Yes.
Yes. All right. Now let's look at graph number 2. Even, odd, or neither?
Even?
So it would only, it's close. It would only be even if it went like that, right? It would have to, I guess a good example is that you could take a piece of paper, fold it over, and still have the same graph. So this one is not even, nor is it odd. This does not reflect across 0, 0, does it? So this would be, oh, sorry. Neither, neither. Okay, and the last one. Even, odd, or neither?
Odd.
Odd. Here's the origin. If I put a point here, it reflects across the origin there. So this would be odd. Okay. So those are the definitions of even and odd functions. And believe it or not, they will come back to you in pre-cal and they will come back to you in calculus, knowing what even and odd means. All right. So let's continue figuring these guys out. So actually, I'll leave it up to you guys. Go ahead and try out number 2, number 4, and number 5, and tell me if they're even, odd, or neither. I guess I could put Carl to work. Yeah, you can do 3, 4, and 5, right? I mean 2, 4, and 5, right?
Yeah.
Yeah, cool.
Let me go erase what I already did for him.
Oh man.
Oh, it's not a big deal. It's 2, 4, and 5, right?
Mm-hmm.
Whole rate.
So I made this snack mix with leftover stuff in my pantry.
Mm-hmm.
There's almonds, chickpeas, cranberries, and M&Ms. Look at
And
that.
drugs. What? That's weird, Robert. Why'd you put drugs in there?
How do you get through a night class?
Good point. All right. Give you guys a little bit more. And then off.
Whoops. No. Don't call.
All right. I'm going to go ahead and start on number 2. So we want to plug in negative x for every x, which will give us negative x cubed minus 1. Anything raised to an odd power will keep its original sign. So this becomes negative x cubed minus 1. Now not all the signs change, so that this one is then neither even nor odd. And you could probably just write neither. And as always, box your answers. So Robert doesn't have to chase him down. Come back to number 4 in a second, or do number 5 first. So we want to plug in negative x for every x. Which gives us negative x divided by the quantity negative x squared minus 1, which simplifies out to negative x divided by x squared minus 1. Now, you may have seen before if you had something like a fraction that said something like this, negative 6 over 7. you may have seen this written like this, -6/7 with the negative sign out to the side. When you do that, just make sure that you're careful about how you change the signs, right? So in this case, if we were to rewrite this as -x/x² - 1, this is not saying that this is even, right? We have to apply this negative in somewhere to see how the signs change. Now we only have one negative, so we can either put it to the top or to the bottom. And that basically means not all of our signs will change. So this guy is neither even nor odd. All right, let's take a look at number 4. Same deal, plug in -x for every x. That gives us the absolute value of -x. We know that absolute value gives us the distance from 0. So a negative absolute value of a number equals the positive absolute value of the number. So this is equal to the square root, or this is equal then to the absolute value of x. So this is equal to f of x. So this one is even.
All right. Wait, but number 5 is actually odd.
Why?
Check. Do the check.
What's the check? I
Oh,
mean, if I let me grab.
oh, you're
if I
on,
get
yeah.
this-
Like multiply that function by -1 on number 5.
So -1 times x/x² - 1 like this.
Yeah.
I mean, that does give us -x/x² - 1.
Which makes it
Odd? How does that make it odd? Not all the signs changed.
hey, that's why
That's-
rational functions are tricky.
Oh, rational functions are gross. So I guess that means that this guy's odd. Never mind. Based on the trick. I've never seen that before. The trick. -1 times f of x. I mean, that makes sense, right?
Yeah.
So yeah, -x/x² - 1, which is indeed what we got. Yeah, that makes perfect sense. I've never seen that before. That's
Cool, huh?
gross.
Right? Rational functions can be tricky, so be careful with that, guys.
Yeah. You will all hate rational functions by the time you're done with this course. I promise you.
Chapter 5, baby.
Oh yeah.
All right. Cool.
All right, let me back off there. Let you go back to doing your thing.
Fine.
Unless you want me to teach the rest of the section.
Hey.
Don't want that.
Don't want that. I was like,
I'm
if
kidding.
you want to.
I mean, I don't care. If you want me to, I can. I just have to erase the work I've been doing on the next parts.
No. Oh, good. I got it. I guess it's what I'm paid for. Okay. Cool. Well, before we begin the next stuff, any questions so far? Okay, cool. So, no. So for the next properties of functions, we get into increasing, decreasing, and constant intervals on a function. So number 1, a function is increasing on some open interval if for any choice of x1 and x2 in this interval, with x1 being less than x2 and the y value of x1 being less than the y value of x2. So I guess the best way to explain that, just draw a nice little picture here. So here's my graph. And let's say that, all right, here is my function. And then here's x1. And here's x2. These y values up here are f of x1 and f of x2. So all this says by that definition is that it's an increasing interval if the y value of the first x value is smaller than the y value of the second x value. That's it. So here, f of x1 is less than f of x2. So this would be increasing. Okay. And then decreasing, of course, would be the other way. A function is decreasing on some open interval if for any choice of x1 and x2 on the interval where x1 is less than x2, we have that the y value of x1 is greater than x2, the y value of x2. So you can do it again, and just really simple, you can go this way now. And here would be, let's say, x1 and f of x1. And over here would be x2 with f of x2. And this would be an example of a decreasing interval where the y value of x1 is greater than the y value of x2. Okay. And the last one is about constant. So a function is constant on an open interval for all choices of x if the values of y are equal. So for number 3, you would have just a horizontal line. So you would have x1 here, x2 there, where the y values would not change, meaning y value of x1 would be equal to the y value of x2. That's it. So those graphs represent those definitions. So now let's go ahead and apply what we just learned to these graphs below. So for this one, use the graph to find intercepts, domain and range, and intervals of increase or decrease, and whether we're even or odd. So let's get started first. And for A, where is my X-intercept? Where are they located at?
Pi, negative pi.
So negative pi, 0. We're missing one. It's not clearly stated, but it's there.
That would be 0.
0, 0. Good. And then pi 0. Okay. Where would my y-intercept be?
Zero.
There you go. 0, 0. Perfect. And then B, the domain and range. So where would my domain start at? What x value?
Negative pi.
Negative pi, and end where?
Pi.
Pi, there you go. And my range, where would we start?
-1.
-1 and stop at
1.
1. Perfect. Okay, let's see. Intervals of increase, decrease, or constant. So increase and decrease. So whenever you read intervals of decrease, increase, and decrease, you only state x values, and we read the graph from left to right. So from negative pi to negative pi over 2, it looks like the graph is doing what? Increasing or decreasing?
Increasing?
So we're going down this way, right?
Decreasing, no?
Which would be decreasing. So we would decrease from negative pi to negative pi over 2. Okay. And then start over at negative pi over 2 And from negative pi over 2 to pi over 2, the function starts to what?
Increase.
Increase. So from negative pi over 2 to pi over 2, we increase. And then start over one more time at pi over 2. And from pi over 2 to pi, the function starts to do what again?
Decrease.
Decrease. Good. Are there any intervals of being constant? You see any horizontal lines, anything like that? No. Okay. Oh, yeah. And then last piece, even, odd, or neither. Remember, if it's even, it would reflect across the y-axis, meaning I would have a point here. Good. Somebody said odd in the chat. So it's odd because it reflects across the origin. Here I have pi over 2 and 1, and it reflects and gives me negative pi over 2 and negative 1. So this is definitely odd. All right. Perfect. Oh, yeah. My math lab is stupid. So your intervals of increase and decrease might be put, it may want bracket notation. Remember that from last semester, Carl?
Unfortunately, yeah. It's pretty dumb. Best of luck, folks.
So you're not supposed to use brackets when stating interval notation
Yeah.
or intervals of increase or decrease. So this could be your possible My Math Lab answer. I don't know when it changed and who changed it, but that's what's going on.
Yeah. And that's just not right.
It's not right.
It's not okay.
It's not okay. Okay, take about 2 minutes and go ahead and try this graph out. Find the intercepts, domain and range, increase, decrease, and whether it's even or odd. So try that out. Read the blueprint in My Math Lab for sure. Okay. So your x-intercepts are at 1/3 and 0. And then again, one's not clearly shown, but we can assume that it's at 2.5 and 0. And then your y-intercepts at 0 and 1/2. Your domain is -3 to 3. Range is -1 to 2. You have an interval of increase from 2 to 3. Decrease from -1 to 1. And then constant intervals from -3 to -1, and then 1 to 2. And this is definitely neither. Any questions on that? Yeah. Everybody good with this one? Yeah. One yes. Perfect. All right. Let's keep moving then. Yes. All right. Coming in. All right. So next, this is about local maximums and local minimums. Basically, a local maximum is a high point on a function. So I guess, like I said, I can do diagrams for everything. So for A, if you had a local maximum, let's say we had some function like that, A, like the one below. This point, and actually this point, would be considered local maximums. So it's just a local high point on a function. And it's where the graph changes direction. And then B would be for a local minimum. So I guess I can even include B on this one. Our local minimum would be a low point on a graph. Local minimum. And this would also be where your graph would change direction. So that's all it is. Local maximums, local minimums. And now looking at the graph below, all we want to know is if we have a local max or a local minimum, where they are. So for the graph, the first graph, we see that we have a low point where the graph changes direction. And when I say change direction, I mean the graph goes from decrease to increase. So this point at -2, -1 would be considered a local minimum. And then the high point, pi/2 and 1, and again, the maximums, the local maxes and mins occur where the graph changes direction. This goes from increase to decrease. This would be considered our local max. All right. Nothing crazy, right? Not bad. All right. I think that's how we wanted to find, right? Local max, local min. Good. Okay. And then the second graph, we see that the points -1, 0 and 1, 0 are both going to be our local minimums. Those are our lowest points on this graph. And then the point 0, 2 is going to be considered a local maximum. All right. And since the graph doesn't get any lower than 0, our local mins can also be considered absolute minimums because the graph is not going to get any lower than those points. So if we had something called an absolute maximum, we would have a graph that would look something, let's just say that my graph is a parabola. The point at the very top can be considered a local max, and it can also be considered an absolute maximum, meaning it is the absolute highest point of that graph. So local min, local max, and then you have absolute min, absolute maximum.
I'm sorry, can you describe the absolute max? I was kind of dozing off for a second. Sorry.
Dozing off.
Sorry.
Oh,
I'm sorry.
you're good. So an absolute max is basically the highest point on the function. Like it's not going to get any higher than that, right? So if I drew, let's see, well, I already drew that, but if I drew this and I had something like this, like that, and like this, these would be considered local maximums, and this would be considered the absolute maximum because it is the highest the function goes. The absolute highest.
Thank you.
Look at these funky graphs.
You won't be able to find those for certain until calculus.
Ah, for sure.
And there would be no local minimum.
On
Right?
this funky graph that I drew, these would be those would be the local minimums.
Okay, got it.
Yeah. Okay, perfect. So that's local max, local minimum, absolute max, absolute min. Any questions? Nothing crazy yet. Yeah, guys, smooth sailing on these sections, right? Okay. Last 2 pages. Look at that. Oh my goodness, the secant line's coming up. Okay. So now we get into something called the average rate of change. What this formula can do is find the slope between any 2 points on a graph, which means that there is no difference than the average rate of change formula and the slope formula that you all grew up with, right? So here is the average rate of change formula. The one main difference is that this is in function notation. But like I said, this is no different than the one you're used to, not y. M equals y2 minus y1 over x2 minus x1. You guys remember that? That's old, right? Old school. So all this is, the average rate of change, is finding the slope between 2 points on a function, and it's in function notation. But just so it doesn't look too difficult, just know that this is just a basic slope formula. So what we want to do next is find the average rate of change, or find the slope between 2 points on a given function. And our function here is 3x squared. So what I like to do is label everything. Since our average rate of change is f of b minus f of a over b minus a, I like to label the x values we're given. So 1 is going to be a, and 3 is going to be b. And now, to find the average rate of change, we're going to have f of b, which is 3, minus f of a, which is 1, over b minus a, 3 minus 1. Okay. And all we need to do now is find out what the values of f of 3 are and f of 1 are by plugging 3 and 1 into the original function, which I can do a little side work below. F of 3 gives me 3 times 3 squared, which will give me 3 times 9, which is 27. F of 1 gives me 3 times 1 squared, which will give me 3. This becomes 27 minus 3 over 2, which gives us 24 over 2, which gives me 12. So again, what we just found was the slope between 2 points from when x is 1 and x is 3. The average rate of change between those is 12. And just so it doesn't look like all we do here is crunch numbers, here is just a little visual of what you have found. So remember, we're dealing with the function 3x squared. 3x squared is the graph of a parabola. And if I were to plot my x value of 1 here, and then my x value of 3 here, their y values, f of 3 and f of 1, all we have found, and I'm going to zoom in, is the slope between these 2 points. The slope is 12. That's it. So the average rate of change between those 2 points is 12. So just a picture, just to help you out, add a visual to all of these numbers. Okay. And now just do it again from 1 to 5. There's A, there's B, average rate of change, f of 5 minus f of 1 over 5 minus 1. We already know what f of 1 is. We found that above, but for f of 5, just do some side work down below. 3 times 5 squared. That'll give me 75. You get 75 minus 3 over 4. 72 over 4. What is that, 18? And there you go. So now when x is 1 and x is 5, the rate of change between those 2 points is going to be 18. That's the slope. And that's how rate of change works, guys. And to keep it easy, all you're doing is finding the slope. Oh, man. Any questions on that page? So if you don't remember the average rate of change formula, then just remember the slope formula, because they work the same way. Or basically, they're the exact same thing. Okay. All right. The next thing we're going to get introduced to is called the secant line. It is a line that runs through 2 points on a graph or on a given function, right? So down here, if we're given a function or a graph, I could just say given the graph of a function. And if we have 2 points, well, there is always a line that can go through any 2 points on a function, and that is called the secant line. And what we just learned is by using the average rate of change, you can find the slope of the secant line, which can help us find the equation of the secant line. So up here, all this states is that, well, if these 2 points can fit to a secant line, then the slope of the secant line shares the same formula as the average rate of change. F of B minus F of A over B minus A. So all we're going to do in this next example is find the slope of the secant line and find the equation of the secant line of a given function. Okay. So last example, guys, look at that. Woohoo. So given g of x equals 3x squared minus 2x plus 3, find the average rate of change from -2 to 1. So before we begin, I like to label. Here's A, here's B. And for number 1, the average rate of change, this is function g. We're going to have g, oh my goodness, right. I'll bring this down a bit. There we go. G of 1 minus g of A, or g of B minus g of A. So g of 1 minus g of -2 over B minus A. And just like before, go ahead and do some side work down below. Find out what g of 1 is and find out what g of -2 is. And you'll get 3 times 1 squared minus 2 plus 2 times 1 is 3. And then 3 times -2 squared minus 2 times -2 plus 3. And that's 3 minus 2, which is 1. So this is going to be 4. And then that's 4, that's 12, that's 16. Is that 19? Right? 4, 12, 16, 19. Okay, cool. So you'll get 4 minus 19 over plus 3. And we get -15 over 3, and we get an average rate of change, or a slope, of -5. Okay, so once again, nothing different. It was just the average rate of change from one x value to the next, which also means it's the slope of the secant line. So there are 2 ingredients to create the equation of a line. You need a slope and you need a point. Well, we just found the slope. It's -5. Next thing we need to do is find a point, which we've kind of done already. So if you look at number 2 above, this is giving us the points -2, g of -2, 1, and g of 1. Well, did we already find out what g of -2 and g of 1 are?
Yes.
Yes. So let's go ahead and fill those out. I'd have a point at -2 and 19, and then 1 and 4. Okay. So I'll say it again. The only 2 ingredients you need to create the equation of a line is a slope and a point. Here we have 2 points, so you can choose whichever one you want to work with. So this is going to lead us on to number 2, and I'm going to say equation of the secant line. And this is going to use this formula that I've given to help you find the equation of the secant line. This is called the point slope formula, because once again, it's telling you the 2 ingredients you need, a slope and a point. It's all in the name. So I'll rewrite it here. Y minus y1 equals m times x minus x1. And what point do you want to use? -2, 19, or 1 and 4?
1 and 4.
1 and 4, good. 1 and 4. And we know our slope is -5. So I finished off this formula. Y minus 4 equals my slope of -5 times x minus 1. Look at that. And all I have to do is solve for y. y minus 4 equals negative 5x plus 5. Add the 4 over, and y equals negative 5x plus 9. This is the equation of your secant line. Look at that, kids. Not bad. So again, I can always draw sketches, right, of what we just found. Again, we have another quadratic function, 3x squared minus 2x plus 3. Probably looks something like this. And what we have found is the line between negative 2, 19, which I'll just put there, and 1, 4, which I'll put there. And this would be the secant line that goes through that function. Of course, I can make it look prettier. I have Desmos. Let's go check that out. So I'm just going to type in everything I have here. Close that, close that. I need to go back to my normal restrictions. Ooh, how about negative 10 to 10? Might have to change that. And how about negative 10 to 10? Still might have to change that. And I'll type in both functions. 3x squared minus 2x plus 3. There's the quadratic function they gave us. And now here is the secant line that we found. Negative 5x plus 9. And look at that. There's the points they gave us. Negative 2, 19, 1 and 4. Here's the secant line that goes through both of those points. So we found the slope of that line, and then we found the equation of that line. So there you go. I couldn't get any prettier than that, right? So that's everything we found. That's the visual to what we have found using the average rate of change or the slope formula and the equation of a line. Yeehaw, guys. Okay, that was 3.2 and 3.3. Any questions on that before heading out?